So good morning, everyone. I'm Vijay Xu. Welcome to the bi-weekly Lighting Talk series on smart city research. And this talk series funded through UT School System Project. So for every other Friday this semester, we will invite speakers from academia, industry, and communities to share research advance and the needs related to smart cities. So if you're interested in this topic, please feel free to visit our website for our past and future talks and also other activities. Our website is smartcity.tech.utexas.edu. We will record every talk, and so in the website you can also review the talk videos, the video from past talks as well. So for today, we are excited to have Dr. Aya Farahi. Aya is a new assistant professor in the Department of Statistics and Data Science at UT. He is a co-founder of the Data Informed Cities for Everyone, a multi-institutional research collaboration that uses data to inform budget planning, resource allocation, and policy evaluation in urban settings. He also has successfully collaboration with the World Economic Forums and the cities of Detroit with his research works. His talk today is on quantifying and mitigating sources of bias in AI decision support systems. So without further ado, we'll pass mic to Aya.
Thank you. Thank you so much for the introduction. Yes, I'm a new faculty member here at UT Austin. I joined in July. So hopefully this talk is going to give you a flavor of what type of research question I'm thinking about and what type of research question I'm excited about. Hopefully we are going to talk a lot during this semester and next semester and initiate new projects. So today I'm going to talk about the fairness and trustworthiness of algorithms and how we can quantify them and how we can make sure that, yeah, go ahead. Is there any question? Okay, sorry. So I'm going to talk about the trustworthiness and fairness of algorithms, especially I'm focusing on AI decision support systems. So actually, before jumping to my talk, let me take just a few seconds and talk about my research. So my research consists of two different elements. In the first component, I am mostly doing a lot of theoretical works. I'm interested in developing theoretical frameworks to identify, quantify, and mitigate different sources of bias in AI decision support systems. And on the applied side, I'm deploying AI solutions to problems in urban planning, decision-making, and policy evaluation. At the same time, I'm also very excited about the computational solutions, especially when it comes to the data science. So far, I have released 3 different software packages at the disposal of the community. Today, I'm going to talk about this specific package Kite, which is designed for the auditing purposes to help us to better understand and quantify the trustworthiness of predictive models that are employed in the decision support systems. All right, so in this talk, I'm going to start with talk about some of the projects that I'm currently doing with the city of Detroit to motivate why we want to look at the fairness and trustworthiness of algorithms. Then I'm going to develop a framework and talk about actually how we can quantify them in a decision support system. And then I'm going to talk about how we can integrate the entire system in an AI decision support system and how we can make sure that the solutions that we are providing to the community is fair and trustworthy. All right, so in early 2020, Donai Kutra, who is one of the faculty member at the University of Michigan, and myself co-founded Data Informed Cities for Everyone. So this is a research collaboration, and the idea behind this research collaboration is to partner with the city governments and nonprofits and help them to develop and deploy data-driven solutions to some of the emerging challenges they have in their community. Especially, we want to make sure that we realize the full potential of the smart cities. And the overarching goals of our partnership are to provide AI support solutions to inform budget planning, resource allocation, and policy evaluation. Today, I'm going to talk about one of the projects that we are doing with the city of Detroit, but we have several ongoing projects with them. So in this project, I'm going to focus on degrading infrastructure in the state of Michigan. Actually, if we look at the data, we see that the state of Michigan is ranked second to the last in spending per capita when it comes to the roads and infrastructure. And actually, if we focus only on the city of Detroit, we see that the situation is even worse. City of Detroit is among the top 10 worst cities nationwide in terms of its road condition. So for example, in the right-hand side, I'm looking at the percentage of roads that are in poor condition for the city of Detroit and the city of Austin. For Detroit, we are looking at the number that is around 56% as opposed to 18% for the city of Austin. So the idea is that we want to help the city to allocate their resources better, and hopefully we want to bring this number to be below 30%, to be more consistent with nationwide numbers, all right? But there are a lot of challenges within the city of Detroit. And the most important challenge is the fact that they don't have enough resources to resurface all the roads that are in poor condition. So we have to identify the bottlenecks in this project and try to find a solution to save money and save time for the city. So one of the most time-consuming and expensive tasks is the road assessment. Typically, the city have to hire a contractor. This contractor have to go to a site, perform some measurement, report back the data. The city is going to aggregate this data, and then the policymaker are going to look at the data, quantify whether a road is in good condition or poor condition, and then they are going to come up with their solution. So the idea is that we want to automate this process and reduce human in the loop. That hopefully it is going to save time and money for the city. So to initiate this project, the city collected around 4 million images across the city, and every 6 months they are going to get a new set of images to see how the roads are going to degrade over time. Then we are going to pass these images to a machine learning algorithm. This algorithm is going to identify the location of cracks and potholes across the city. Then we are going to measure the properties of these cracks and potholes. We are looking at the size, the depth of these cracks, and then we use this summary information to quantify the condition of each road. Essentially, it is going to be a classifier. We are going to say whether a road is in a good condition or it is in a poor condition. Once we have this classifier, we are going to pass the output of this classifier to a decision support system. So the idea behind this decision support system is that we want to prioritize the road segments that need to get resurfaced during the next batch of maintenance cycle. The city does not have enough resources to fix all roads which are in poor condition. So we have to prioritize a subset of them. To do that, we want to maximize the benefit for the residents. So we are going to combine the road condition data with population occupancy data. We are going to look at the public assets that are owned by the city. We are looking at the bus routes and the ridership data. We look at traffic volume data and combine all of these things together to come up with a utility function. And then by maximizing this utility function, we can come up with our solution and prioritize the roads that need to get fixed. And if they get fixed, they provide the maximum benefit for the residents. And then we are going to visualize our results and our solutions to the policymakers through a UI system that we are developing for the city. And hopefully the decision makers are going to use the output of this system to make their final decisions. All right, but we have to be very careful about the potential implications of this AI system that we are developing and how it is going to impact different populations and different groups across the city in a long run. And we have seen news and headlines about the potential negative implications of AI systems once they are deployed into our society, especially the negative impact of these AI models on the underrepresented and underserved population. And this is the type of thing that we want to avoid with our AI system. We don't want to exacerbate the gaps and the biases that we see in the historical data. We want to make sure that we are reducing the gaps that we are seeing in our data. All right, but what type of gaps we have in our data? So essentially, we want to make sure that the solution that we are providing to the city is fair and trustworthy. So let's actually look at the historical data that we have. Here on the y-axis, I am showing you the distribution of the average road quality for census blocks. And I stratify the census block based on the poverty rate and the household income. Something that you can immediately see here is the fact that the poverty rate and the household income of your neighborhood determines what type of road condition you have. And this is exactly the type of situation that we want to avoid. And we want to make sure that our AI system and our solutions are not going to exacerbate these bias and these gaps that we are seeing in our data. All right, so we have to first define what exactly mean by fairness and how we can measure the fairness across different socio-demographic groups. How we are going to approach this problem, we are going to say that, okay, there is no fair solution. Essentially, at the end of the day, after doing many run of the decision making, we want to reach into a fair solution. We start from an initially unfair solution and we want to reach to a fair solution. And how we are going to quantify it? Basically, we are going to stratify our data based on the road condition. We have one set of neighborhoods who have a good road condition and one set of neighborhoods which have a poor road condition. And we are going to look at the distribution of the socioeconomic feature of those neighborhoods. And here, for example, on the right-hand side, you can see that the joint distribution of the socioeconomic features in neighborhoods who have a good road condition and poor road conditions are not on top of each other. It implies that there is a distance between these two distributions, and by measuring the distance between these two distributions, we can quantify how much unfairness we have in our data. And the idea is that after several iterations of decision making, we want to bring these two distributions on top of each other. So by measuring the distance between these two distributions, we can quantify how much unfairness we have in our system. All right, so now we can look at the different algorithms, different decision-making algorithms, and evaluate how they are going to reduce the unfairness in our data. So here on the right-hand side, I have a measure of the distance between these two distributions as a way to quantify the unfairness in this urban setting. And the idea is that can a decision-making system reduce this discrepancy, or they cannot. So here, the red line, it is showing a utility-based decision support system. So if we only maximize the utility function, actually we cannot reduce these biases and the gaps that we are seeing in our data. So the second solution is a random solution. We say that, okay, forget about the utility. We are going to randomly pick road segments and we are going to propose them to the decision makers. Actually, this solution can reduce the biases in our data. It can reduce the unfairness that we are seeing in our data. But unfortunately, it is not going to look at the utility function. So it is not going to provide the maximum benefit to the residents. So this solution is not good either. So we decided to combine two different scores. We have one fairness score and one utility-based score, and we are going to optimize both of them simultaneously. So here we are both maximizing the utility function and fairness score, and we can show that in a finite amount of time, we can reach a fair solution using this algorithm. All right, so far I was talking about how we can make sure that a decision maker can make a fair decision and how we can reach into a fair solution. But in an AI system, we have different sources of bias that can have an impact on the decisions that we are making. So really we have to divide we have to look at different elements of this AI system and identify different sources of bias. So I divided this AI system into three different main components. First is the data that we are collecting, and we use this data to train and test our models. And then we have models that are going to digest this data, make a prediction, and the decision maker is going to use the output of these models to make some decision about their underlying population. All right, to simplify this process, I divided this decision making into 5 different subtasks. First, we have to identify a task, and then we have to construct an objective function. First, we have to make sure that the objective functions is not biased by construction, and the question that we are asking is fair by construction. After we make sure that the question is fair and the objective functions are not biased, we have to collect some data. But data is not always clean. data can be noisy. The noise can be correlated with protected features. It can be sampled in a biased way. We can have missingness in our data. This missingness can be correlated again with the protected features that we have in our data. So we have to be very careful about our data. But today I'm going to mostly talk about models. The central part of any decision-making systems are the models. These models are going to essentially digest the data, and then they are going to train themselves, and then they are going to provide some information for the decision maker. And this is the job of us as a modeler to make sure that the information we are passing to the decision makers are trustworthy. If these information are not trustworthy, it is impossible for the decision makers to make a fair decision. So trustworthiness of predictive models is the necessary condition, but it is not the sufficient condition for algorithmic fairness. So today I'm going to talk a little bit about how we can quantify trustworthiness of predictive model. I'm going to define trustworthiness, and then I'm going to propose an auditing tool that we can use to evaluate the trustworthiness of predictive models. All right. All right, so I'm going to look at the trustworthiness in the context of binary classifiers. You can take the same idea and generalize it to non-binary classifier and actually to the regression models as well. But for the simplification, today I'm going to focus only on a binary classifier. All right, so suppose you have a model that is going to predict the probability of developing cancer for a subset of patients if they are given a treatment T. And the question is that whether this predictive model is providing trustworthy information or not. Suppose that this predictive model is going to predict that with 50% chance, a subset of patients are going to develop cancer. If this information is trustworthy, then indeed 50% of my patients have to develop cancer. If this number is 40% or 60%, it implies that this number is not trustworthy. I cannot use this information to make any decision. All right, so suppose that this subset of patients consists of 10% from a minority group A and 90% from a majority group B. Then I'm going to run an observational study to evaluate the performance of this model. And I find that 95% of people in group A and 45% of people in group B have developed cancer. So actually, if we look at the numbers on average over the entire population, 50% of my patients have developed cancer. So on average over the entire population, this model is trustworthy. But if we are concerned about each individual subgroup in our data, then this model is not trustworthy anymore because the prediction of this model does not match the frequency of developing cancer for each subset of my patients, right? And the impact of this type of miscalibration, mistrustworthiness, is more damaging on the underrepresented population than the majority population. So for example, in this clinical setting, we don't want to distribute resources equally across our entire population. We want to make sure that each patient gets resources based on their needs. So showing that a model is trustworthy on average over the entire population is not sufficient. We have to show that a model is trustworthy with respect to every subset of our population. And how we can mathematically model that, actually we can say that whether the prediction of the model matches the frequency of future observations for every subset of the population or not. And then we can develop a hypothesis testing framework by using this equation. So actually, let me give you an example of what is happening here. Suppose that I have a predictive model that predicts the likelihood of developing cancer. And it predicts that with 50% chance they are going to develop cancer. So indeed, when I'm going to collect data, they should develop cancer with 50% frequency, all right? So suppose that the input of this predictive model is age, genomic expression, and gender. But a decision maker comes and say that, okay, I don't care exactly what goes into your predictive model. I want to make sure that your model is trustworthy with respect to age, gender, race, and income level of my patients simultaneously. Otherwise, I cannot use the output of your model to make any decision about my patients. So it doesn't matter exactly what features you're going to feed into your algorithm. As long as it is going to give me trustworthy information, respect to the features that I care about, I'm going to use your model. Otherwise, I'm not going to use your model and your model is not trustworthy. So actually we have developed an open source package to solve this problem. It is called Kite, and basically it uses this idea to quantify the trustworthiness of predictive models. So these predictive models are going to make a probabilistic prediction. We are going to pass this predictive model through a hypothesis testing framework. It is going to tell us whether our predictive model is trustworthy or untrustworthy. And if it is not trustworthy, then it is going to quantify how much untrustworthiness we have in our data, in our model. So essentially, if you give me two models, I can tell you which one of them is less untrustworthy. So we can perform all sorts of model comparison. And if a model is untrustworthy, we can pass it to a calibrator, and this calibrator is going to estimate biases both at the population level and at the individual level. So we can say that for each individual, how much predictive bias we have for this model, right? And then we can correct for this predictive bias, and we can this model trustworthy. All right, so this is basically showing just one example of what is happening within this package, this auditing package. I took the Compass recidivism data set, I trained the random forest classifier, then I performed hypothesis testing. I asked whether this predictive model is giving me trustworthy information with respect to age, gender, and race or not. So here, the only thing that you need to take away from this chart is the fact that p-value is close to 0. If the p-value is close to 0, I have to reject the null hypothesis, and I can say that this model is untrustworthy. So now, because this model is untrustworthy, I'm going to pass it to a calibrator, and the calibrator is going to estimate the bias for each individual person I have in my database. All right, so here each data point is correspond to one person in my database, and it is going to estimate how much bias I have for that person. Once I stratify the data based on the race, gender, and age, I can quantify how much bias I have at the group level, right? And you can see that these biases are not constant. It is not just one number that I can correct for. It really depends on the race, age, and gender simultaneously. All right, so I think I passed the 20 minutes, so let me actually conclude here. So hopefully it gave you some flavor of what type of research problems I'm interested in. And I would love to get your feedback and start talking to you and explore ways in which I can contribute to this community. So again, just to remind you, my research goals are to develop theoretical models and implement auditing algorithms to quantify and mitigate biases in an AI decision support system at all levels, data, modeling, and decision. Today, I talked a little bit about how we can quantify fairness of decisions and how we can make sure that we can reach to a fair decision in a finite time. I talked about the trustworthiness of the model, but I'm also doing a lot of work on the data side. So, and I'm hoping to bring AI, fair and trustworthy AI research to the forefront of urban planning and decision making. All right, thank you so much for your attention, and I'm happy to take any question that you might have. Thank you.
Thank you very much. It's a very interesting talk. So if you have any questions, please feel free just to unmute yourself, and we'll have 5 minutes for some questions. So one question to get started is, I'm curious, how do you have a challenge to communicating those statistical funding with the decision makers during your collaborations, who may be not so technical savvy with numbers?
Sure. In terms of decision makers, the person that we were working with actually was one of the graduates from the University of Michigan, and then he was a data science fellow at the mayor's office in the city of Detroit. So he had a lot of a background and knowledge in analytics, and we could very easily talk to each other. But it is a very good question how we can communicate these results with the lay audience and decision makers who doesn't have this kind of background. So I don't have a lot of experience in talking to the decision makers, and the only decision maker that have been our point of contact has a lot of background in analytics, and it was a very easy way of communicating and convincing each other that these algorithms at least can contribute to the society. And at the same time, we are running a bunch of simulated data set and showing the output of this simulated data set to show how it is going to benefit the residents in a long run. And hopefully we can come up with a way to quantify and communicate this quantification with the decision makers. But typically it is a very hard problem how to communicate decision makers. And typically you have to build a trust between the decision makers and yourself if you wanted to work with them. And building this trust, it is, I think, the hardest part of working with especially the government organizations.
Thanks. I think there's another question in the chat.
I'm curious to know if this algorithm detects different type of cracks on roadway and how it detects severe ones. So actually, we in our algorithm, we had like different types of cracks, like crocodile cracks or longitudinal cracks or horizontal cracks. And we had a way to basically, we had a classifier to classify which type of cracks we have in the street. And to quantify the severity, we are looking at the area that is covered by these cracks. We are looking at the length of these cracks as a proxy for the severity. And then we are talking with the decision makers who are using this actual data. Basically, we are trying to tune our algorithm to the way that they think about this problem and how they quantify the severity of this problem. Because at the end of the day, we are concerned about a binary classifier, whether a road is in a good condition or whether it is in a poor condition. We are not very concerned about quantifying exactly the severity of these cracks and potholes. Typically, it is very easy to say whether a road segment it is in a poor condition and require maintenance, or it is in a good condition and does not require a lot of maintenance in the next, for example, 6 months or 1 year.
I have a related question, I think. I'm curious if the engineers from the city are able to adapt their designs based on this, image information based on your classification, or do they need to go then to those road segments and do some type of physical testing to be able to adapt their designs?
So actually, this is one of the things that we discussed with them to basically tune our model and make sure that we are providing, for example, unbiased prediction of the condition of each road. So basically, they have not collected this data yet, and we don't have this data, but basically they are going to look at a subset of the road segments, and they are going to perform their own evaluation, and then we are going to compare our evaluation with their evaluation to make sure that everything is aligned with the evaluation that they had in mind. So this is one way of just testing our algorithm, make sure that what we are going to produce for them is useful for them, and it is aligned with the way that they are thinking about this problem.
Excellent, great presentation. Thank you.
And if you are interested about any aspect of this work, I would love to talk to you in the future and see and explore the ways in which we can collaborate with each other. So I'm very new to the UT Austin. I joined in July of this year, and still I'm learning my way around the campus and around the city. So if you are interested in this topic, let's go and chat, whether through Zoom or in person on the campus.
It's great. It's a very good talk. So I think we're right on time for today. I'm just putting the website in the chat. So if you're interested, you can visit our website, and we'll post the presentation video there. And if you want to reach to us, you can go through the website as well. Thank you for everyone attending today. We'll see you in our next events.
Thank you so much, everyone, for joining.
Thanks, Aya. It's a wonderful talk.
Thank you. Have a good day.
Bye.
Bye-bye.